Okay, thanks. First of all, thanks to Shiva and other organizers, and also ICTS for getting me here and this opportunity. And thank you all for coming. Okay, so the title of my talk is What is Symplectic Geometry? It's a field that I work in, and hopefully by the end of the talk, I would have introduced some objects that are of interest to us symplectic geometers, okay? And stop me and ask questions whenever you have them. Yeah, we can go back and forth. Okay. So let's start with a mountain. Okay, there's a mountain, M, and that little pink thing is me. I'm standing on it at some height. And then I'm having a very lazy day. So today I don't want to climb up or climb down. I want to walk in the same height. Okay. So no least effort walk I want to take. And then I have another friend. She's meeting me after some 42 minutes. And she's like, she wants to find out where I'll be after 42 minutes. So she wants to write a function down of the path of my movement. I told her where I'm starting from. Okay. So that she wants to do. How does she do such a thing? Okay. So first of all, there's a technical name for this line that I'm walking on. If I look at the height function, so at any point of the mountain, there's some height in some units. And of that function, there are these objects called level sets. So they're all the points on the mountain that map to the same constant value. Okay, so say 500 meters. Okay, so I'm starting at 500 meters. I should continue being at 500 meters, which means I want to continue walking on a level set, which is denoted like this. It's all the points whose h value is c. Okay, so I want to walk on a level set. And we want to develop a formula for that walking. So how do we do this? Let's rewrite this picture a little bit. So if I think of the mountain as the graph of this function, so I can have the height function just on R2, like the base, okay? And then each point on the mountain is a point on the graph. So it's some x, y, and one value of h. Then this mountain becomes the graph of one function, h, same function we had before. And then we can draw this thing called a contour plot, where each line is all the points that map to the same value. Okay, I haven't written the values, but each of them you can think. So the one I'm on, let's say, is 500 meters. Then the other one is 600. The one below is 400, like that. Okay. So these are contour plots. And what I want to do is I want to exist on exactly one line of in this picture of the contour plot. So how do we develop a formula for that? Okay, so maybe you have heard this, maybe you haven't. So it's a new fact, is that there's a gradient of the function, which is just the two partial derivatives. Okay, that gradient vector at a point will be perpendicular to the level set. So there I've drawn one picture. There's a vector and it's perpendicular. Okay, so if you don't know this, this is fact I'm giving you. So if we know this fact, then what we can do is, if we rotate my gradient vector by 90 degrees, it was perpendicular, now I rotated it, then I get the vector I want to, my speed should be in when I'm walking. So let's call that xh, okay, and xh will be the vector that I want to walk along, and at each point it will change, okay. So that is, if we want to do that. Now let's see how to do rotation. In R2, if you take xy and rotate by 90 degree anti-clockwise, you get y minus x. So 1, 0 will go to 0, 1. Or you can take some other orange color vectors. So this xy will go to y minus x. Okay, that is the rotation. So by that formula, if we rotate, so our gradient was these two partial derivatives at any point xy, right? Then if you rotate it, you have to put minus del h del y and del h del x. So that is the vector. Okay. So now at each point on R2, I have a vector and I want to travel so that I'm always tangent to this vector. Then I will remain on my level set when I'm walking on my mountain, right? Okay. Okay. So let's see how to write that out. So this was the information we have. We have gradient and we have xh, which is the rotated one. And then so now we want a path. What is a path? It's a function from r to r2, right, wherever I'm walking. And let's call its coordinates xt, yt. And when I take the derivative of that path, so x dot t, y dot t, so that's a t derivative. I want it to be xh. Then I'll be walking in, I'm always walking tangent to xh. Make sense? Okay. So then we get this formula, x dot is equal to minus del h del y, and y dot is equal to del h del x. So this system of equations is called Hamilton's equations. So man has many equations. This is his equation for mechanics. Okay, these are called Hamilton's equations for mechanics, and so this rule will let me now walk. And if my friend knows my initial position and solves for these two, and somehow knows the height of the mountain function, then and solves for this, she can predict where I'm standing after 42 minutes. Agreed? Okay. Now what are we doing with all this? Hello? Okay. Okay. So this is the equations we care about, and what are we doing? So we're now looking, so it's called Hamiltonian flow. So this h, that the function is dictating how I move, right? The function of the height of the mountain. So that is called a Hamiltonian function. It's just in this context, it's just a function, but in this context, we call it the Hamiltonian. And now we have these paths which are solving this equation. At each point, the derivative has to be equal to the vector xh. Okay, that is that equation. So then if we look at paths like that, they look like something with some starting point. Okay, so the starting point, we'll call it the initial condition, and it is some point P. Now, if I start at some other point P, I can get a different curve. So there's some 4 curves I drew. They can all be different paths of motion depending on the starting point with the same function h. So for what we can do is, now we can, now we were looking at for each starting point, there's a path. So what we do is fix a time t, 42 was the number we started with. Okay, so for time 42, all the points, whatever starting point, me, any other point of the mountain, if we move it for 42 minutes, where do we land up? That will give us this other function phi t. So t, you can change the value of time. So phi t, and the function will depend on h. So this thing is just saying that for each point, move it along the path that starts at that point for t amount of time. So this thing is usually called the Hamiltonian flow. So it's a flow on the, so every point on the mountain is moving according to this rule, if you just let it be. Okay, so revision. So h was a function from R2 to R, and we'll call it the Hamiltonian. And this xh, which we found by taking the gradient and then rotating it, is called the Hamiltonian vector field. A vector field is at each point you have a vector. Okay, so here at each point you can evaluate xh and you'll get a vector. And then we had a flow, which was for any time. So I've taken time only between 0 and 1. You can take other things, but so for any time between 0 and 1, you will get a function from R2 to R2, which is every point is moving together according to the rules by xh. Okay, and that movement was given by this equations, and this is picture of Hamilton, which all this is named after. Okay, okay. So all this happened. Now you might ask, okay, this is some random situation where Ipsita was standing on a mountain. Why do I care about it? But there are a lot of points, like physical systems often behave like this. Okay, so let's talk about that. So why do we care about these equations at all? So what sort of objects want to move on a level set is the question. Like lazy Ipsita is one, but the other thing, like more interesting objects maybe. So suppose, okay, so we want to talk about spaces which are called phase spaces, okay? So instead of just recording the position of a point, we will also record its momentum. Okay, let's learn by example. So suppose you have a point moving on a line, okay? There's a line and it can move wherever it wants, however fast it wants. Then position value x can be any real number, correct? Okay. And the momentum, let's fix mass equal to 1 because I don't want to go into that. So let's fix mass equal to 1. Then momentum is actually just the velocity. And the velocity can be any vector pointing left or right. So again, it is one more real number. Okay, one-dimensional vector is real number. So position and momentum together. So the phase space is r cross r is r2. So phase space for a point moving on a line is r2. Clear? Okay. Now, if this is the point that's given, what we can think of as our, oops, okay, what we can think of as, so the previous story, instead of h being the height of a mountain, I could tell you that h is some total energy, okay? And Newton's laws and other things tell us that unless provided by some external force or something, if a particle does not want to change its energy state. So h, if it's the energy function on this phase space, okay, so now on R2, like on the previous, so let's go back. So here, now instead of R2 being where the mountain was, if you think of it as the phase space of a point moving on R, then h we can think of as total energy, okay? And total energy, a point wants to preserve it while moving. And that total energy, what it is, it'll someone, I don't know, someone has to tell me. I don't know how to obtain it. But once someone obtains it, I can tell you what the paths the particle can move in. Like what is the position and velocity of it. So its movement is actually happening inside the phase space. So the R2 now has extra character. Okay. So we did some things in this space which were little bit, maybe we could do it in a different way. So what we did is we took this gradient object and then we rotated by 90 degree. But you can tell me, I don't know what 90 degree is. And then I'll be like, okay, let's try one more method. So I'm going to try to tell you another method of coming to this vector xh. Okay. Okay. So let's see. So there's this thing called a symplectic form. What is it? It's actually just calculating the area between two vectors. Okay. So if you have two vectors, v1, v2 and w1, w2 on R2, then the area, that parallelogram shaded area, is v1, w2 minus v2, w1. Correct? Okay. So we can write it, we'll denote it like this. Area, I'll use my favorite letter, omega, small omega. So small omega VW is this number. That is the area between V and W. And remember, it's from V to W. If I go from, this is a cross product. Okay. Okay. So then I can also write it like this, where I have transposed the vector V1, V2, and in between I put this matrix 0, 1, minus 1, 0. And if you multiply it, you'll get that same quantity. Okay. So this thing has some nice properties. What are the nice properties? So it's a function that's taking an input two vectors from R2, right? So it's a function from R2 cross R2 to R. The output is one number. And it's bilinear. What is bilinear? So bilinear means in the first coordinate, if I multiply by a constant, then the constant comes out, okay? And in the first coordinate, if I add two vectors, then the values get added. And what is the bi part? The bi part is the same business happens in the second coordinate also independently. Okay, so four things sort of happen. Okay, such a function is called bilinear. Linear is in one variable, bilinear, each vector is happening separately. Okay, so that is first nice property of omega. Second nice property is it's skew symmetric. This you already know by a different name, which is if I invert the order of the vectors, then the value changes. So this is like the cross product, right? So and the cross product had a direction, and the direction would change according to your right hand rule. So this is also saying that. Okay, so this is called skew symmetric, fancy name for this. Okay, and the third property that is nice is that it's non-degenerate. What does this mean? So I've given myself more space. So it says for every vector that's non-zero, we will find another vector that's non-zero, so that if I pair those two using omega, I get something non-zero. Okay, so what is it saying? So let's see how I can do this. If my first vector is v1, v2, if I take w to be minus v2, v1, I'm actually doing what I did before, rotating by 90 degrees. Then I get this square in between. And that square has area v1 square plus v2 square, which is not zero. It's positive for whenever v is not zero. Okay. So for each vector, I will find another vector so that the combination gives me non-zero. Okay. Just a note that this is also the norm square, if you know norms already. Or it's also with the standard inner product, it's v dot v. Somehow all this is related. Just side note that is. Okay. So let's go back. So we had omega with some three nice properties. It's bilinear, skew symmetric, and non-degenerate. And any function which has these three properties on a linear space, so R2 is a linear space, is called a symplectic form. Okay. So now how does this help us? Before I tell you how it helps us, you can actually define such an object on a bigger vector space also. So if you took R2n, then you can look at, so in the previous thing we had multiplication by this 2 cross 2 matrix in the middle. Instead of that, I can put copies of that 2 cross 2 matrix along the diagonal, and then look at the map given by this formula. Okay, it's the same thing, just more coordinates. And that also turns out to be a symplectic form on R2n. Why have I taken 2n? Because of this non-degeneracy condition, you can't do it in odd dimensions. Then there'll be one vector sort of left out, one direction will be left out. You won't have any pair for it. Okay, that's the idea. So this phenomena only happens on even dimensional things. Okay. So this is just side note that you can define this on all dimensions, all even dimensions. And okay, if you don't know what a basis is, ignore this. But what this is saying is you can do some different choice of bases. Instead of taking 0, 1, 1, 0, you do 0, 2, 3, 0 or something. But up to some choice of bases, you'll always end up with a matrix that looks like the top thing only. So the note is we'll only care about, even though I defined some nice properties, we'll only think about this matrix, okay? So we're always multiplying by this matrix in the middle. Okay, so now I defined some fancy map. How does this help us? So let's go back to our problem. On R2, we had an energy function, right? H. Now I'm calling it the Hamiltonian, the energy, the height of the mountain, whatever. So now we want to obtain XH without doing 90-degree rotation. Like, I don't know what 90 degree is now. Okay, how do I do this? So differential is some object we can define. I'm going to cheat and define it like this. For each point P on R2, you compute the gradient and define the differential dH of P to be dot product with that gradient. Okay? You have seen this in some form, I think, but let's take this as definition. Okay, does dot product with gradient. So this map, now I can define XH as the unique vector field. So at each point, vector is there, such that the derivative is the same as evaluating omega with my vector XH in the first coordinate. So how can I define this? Actually, that non-degeneracy condition will give me this uniqueness here. So you have to believe me a little bit. that by saying that this is the unique vector field such that all this happens, that it's actually a definition. Let's do some computation to see we believe this. So in our previous example, so the left-hand side will be equal to this number because I'm taking dot product with the gradient, right? And this right-hand side, what will it be? So it's omega. Let's just put some coordinates, xh1 and xh2, and solve. So if I solve, I get this number. Now I'm going to compare it. Okay. So we have two numbers. So this has to hold for every v1, v2. So therefore, those two blue color boxes and the two red color boxes have to be equal to each other. Okay? Because I can put 1, 0, 0, 1 and evaluate. Okay? So then I end up with this vector has to be the same thing. Remember before when we did all this 90-degree rotation, we actually got the same thing. So somehow using this symplectic form, I'm able to obtain the same vector. Okay? Okay, cool. So do we have a revision slide? No. Okay. But why am I doing this? You'll be like, we all know what is 90-degree. No need to tell us. The problem is, so I gave you a phase space example where the point was moving on a line. But if you've taken any physics classes, you know that that's a really simple example and things get difficult very quickly. So phase spaces don't always look like a line. Okay, but we want to be able to deal with phase spaces that are way more complicated. Let's take more examples. Okay, so phase spaces don't always look like some R2n. On R2n, we know how to rotate by 90-degree all this. But let's take examples. So suppose instead of on a line, your point is moving on a circle. Okay, then your position is now some point on the circle. S1 is circle. Okay. But now the momentum is some speed, which is again, it's just going to be a real number at each point because it's just whether you're going left or right and how fast you're going. Okay, again, we are taking mass equal to 1. So the phase space looks like one infinite cylinder, right? S1, so circle times infinite line. So you get an infinite cylinder. And that clearly does not look like R2, even or any Rn. So what do? The saving grace is that locally, so if I take a very small piece of this infinite cylinder, I end up looking like a small piece from R2. Yeah? So I shouldn't be stupid and take one huge piece. But as long as I'm taking a small enough piece, I will look like I'm standing on R2. I won't know the difference. This is like when I'm standing on the surface of the Earth. The Earth is big enough that I don't really know whether it's curving or doing all this. I just know that locally I'm on something that looks like a plane. Okay, so this looks like business has a name. It's called a homeomorphism. Okay, in fact, in this case, because we want to do some taking derivatives and all, it has to be a diffeomorphism. But okay, but we will just stick to this. Okay. Just think in small patches, it looks like R2 only. So now, okay, so such an object is called a manifold. So what is a manifold? In small pieces, it looks like some Rn. Okay, but when you stitch it up, maybe it has some fancy structure. We don't know, but in small pieces, we know what it looks like. And I'm claiming that knowing that these small pieces look like Rn is good enough to treat the problem we were dealing with before. How do we do that? So my claim is this rotation by 90-degree, I mean, you can make that also happen, but I want to go by the approach of using my favorite function, omega, to do this. What do? So on this, I'm going to define omega. So as soon as I'm in a small patch, okay, so that's called a local chart. Okay, local chart, it's like on the atlas. You have a small, if you have a book of atlases, or I don't know, on your Google Maps, if you zoom in, then you're looking at only one small chart. Okay, so if I'm on such a chart on which I know how to map it to R2n, I will use that matrix multiplication that I did before. If I'm on a different chart, I will use the other weight I have identified it with R2n to do the matrix multiplication. And how is it defined on the whole manifold? Whenever there's overlapping, it has to be somehow consistent. Okay, let's say that out again. So if I'm in this pink color patch and I have two vectors v and w, there's some, and they're sitting at a point P, okay, the base point. So then there'll be some omega P. So somehow this multiplication might slightly depend on the point, but ultimately it looks like that matrix. Okay, and then now if I have this other blue patch and a point P prime, then the function I'm going to use is omega, which depends on P prime. So the function is changing depending on the point. But if I'm in the middle and it's in the blue patch and the pink patch, whichever rule I use, I should get the same number. Okay, if I can do this, then I've consistently defined a symplectic form on my infinite cylinder. Okay. Okay, so okay. So now on a manifold we can define Hamiltonian flow. How do we do this? We have a random manifold M. Okay, it is a symplectic manifold, so it has some dimension which is even. For now, just think of it as 2. Okay, this infinite cylinder. And now define xh as a unique vector field using the same formula that I said before. Whenever you want to define derivatives, it should be same as taking omega product with xh. And by the same reasons as before, this will give you an xh everywhere. Okay, so you have to believe me a little bit, but it works. And so now you can define, somehow I'm gone back to saying all time. Okay, so now that phi, which depends on h, will be the flow. So now we know how to, if we start at any point on M, how to move. Like now my M doesn't need to be R2. I know how to move in any random thing, even like the phase space, which is the infinite cylinder. Okay, so this nice function omega is helping me understand some sort of energy functions on the phase space and how points move using that. Okay, oh, here's an example. So suppose your phase space, I don't know which particle where it is, but somebody told me my phase space looks like a sphere, like the sphere. And then there's some height function, which is just the z coordinate. Okay, and so it goes from -1 to 1, and you want to use that height, that coordinate as your energy function to move things. So if you do all these computations, you'll see that the circle has to, it has to just, the entire sphere has to just rotate around one axis. You can compute all this. And there's Emmy no other. So this sort of maps on things which are sort of, I don't know, there's some more properties. These are called moment maps. And she studied moment maps a lot. And there's this idea of conserved quantities, and under conserved quantities, how things move and stuff. So all of this, she didn't start it in this language. She didn't study it in this language, but she has a lot of work with moment maps. And usually it's in a physics class, I guess. Okay, so now we know how to do Hamiltonian flows on a random manifold with a symplectic form. Okay, cool. Any questions? Yeah, there's a mic I think you have to use. Yes. Okay, so the question, I'll repeat, is can I explain the consistent overlap business again? So let's go back to this picture. So now I said that, so omega on R2 was multiplying by this matrix, but now these patches can look little wavy. So there's some way to identify it with R2. And using that identification at each point, I'm getting this omega P, which is ending up depending on the point P, just because of this identification. And now there can be these patches that overlap. So there's a blue patch and a pink patch. And for each of those, I've identified it with some small piece of R2 in a different manner. Now, if I want my omega to be consistently defined on my full cylinder, that means, so for that point sitting in the overlap, there are two ways to compute this function omega that doesn't have label, unlabeled point. And so the two ways, like according to the blue rule and the red rule, pink rule, should give you the same numbers. Okay, make sense? So whenever there's overlap, there are multiple ways to do it, but a consistent symplectic form on my manifold means that whenever there's overlap also, I should not get clashes. I do one way, I should not get 3, and other way minus 3. Okay, one sec. Cool. More questions? Okay, then we'll move on a little bit. Okay, other. So now I set up all this, and it's some way of understanding some mechanical systems. What do I do with it? Or what questions do people ask? What questions do people try to solve? The first sort of question is, so we were looking at like points moving. So once you've given them this h functions, they're moving around, right? And the path that a point takes is called an orbit. Now, some orbits might come back to its starting point. And we could ask a question that are there any such points? So are there closed orbits? So is there some point that travels and in some finite time comes back to its starting point? Okay, so such questions are interesting. I'll show some cool pictures later. But if you are an engineer or a physicist, maybe you care about planets or other objects moving around in space. And I don't know, so a story will come up later. Suppose you have a satellite, okay? And you spent a lot of money, and now you want to send the satellite into space, and you want it to orbit Earth. You don't want it to leave and go into space untracked, okay? All that money and time will be wasted. Government will be very angry. So you want to make sure that it comes back to its starting point, and you can't send it with infinite fuel to do this. So the best possible thing would be to calculate the h function for around Earth, okay, and then put it in such a point, just like leave it in one of these points such that after some finite time it will come back and the whole thing will repeat. Okay, so closed orbits might be very interesting, so that you don't lose your satellites or other things like this. So if you're studying some other sort of object, if you find closed orbits, point on the closed orbits, you only need to study, like here I've put the time periodicity time as 1. You only need to study it for whatever 1, like maybe 1 year. So for 1 year you need to study it, and after that everything will repeat. So you can save your energy and study only for that time. So periodic points are extremely interesting to us. But once you find one periodic orbit, you're like, how many are there? Okay, are there many of them? Are they big and small? Somehow, so if it's this satellite going around Earth, if I find one whose periodicity is 273 years, so it'll go somewhere and come back. And if its work is to like take pictures on Earth, then it's spending very less time on Earth, near Earth. So I'm not happy with it. I want something with smaller periodicity. Yeah, so you want to know how many orbits are there, how big they are, how fast they come back, all of such questions. Then there's some famous problem called closing lemma, which is slightly related. So remember we said you're always moving on a level set, right? So now consider this toy picture where the level set looks like that blue square. Okay, and we have points moving on the blue square. Now, suppose there's a point which does not come back immediately to itself, but actually comes back near to it. Okay, so the near to it we'll quantify by there's this u, which is some open set where the point P started from, and after time 1 it came back into the same u. Okay, now given this setup, you're like, okay, are there some close by points which actually come back to the starting point? Are there close by points which actually close up the orbit? So this was, okay, so here. So then can we find, maybe it's not even on the same level set, but there's a nearby level set where there are points which are coming back to its starting point. So there are closed orbits. So this setup, I think I forgot to write the names, but this is attributed to Poincaré. Maybe it's a name you've heard, who asked it, I don't know, I want to say sometime in the 1800s, asked such a question of whether if you have a system that's dictated by some vector field. So he didn't consider only vector fields coming from Hamiltonians, but any vector field. And you have one point that's coming back close by. Can you find a point that'll come back exactly to the starting point? And you're allowed to do some changes. So here I said you're allowed to change which level field. But maybe instead of changing the level field, you want to change the function h little bit. So you're allowed to do little bit changes, but by doing little bit changes, can you fix the closing? So that's called closing lemma. And it was important enough that in 1998, Smale, mathematician, announced a bunch of problems called problems for the next century. He thought these are important problems everyone should think about. And this problem in some version appeared in that list. So lots of people have been working on it, and there's special, like more, with some more adjectives. There's a bunch of us working, and so there was a lot of work in, okay, so what did we discuss? We said symplectic manifold has to be even dimensional. So if it's a level set of an energy function, that will be odd dimensional. So this question is somehow about odd dimensional manifolds. And so if the odd dimensional manifold is dimension 1, I think it's sort of easy. Dimension 3, you need to add more adjectives, which I'm not telling you. But after adding some more adjectives, they've been like people working on it for a very long time. In some cases, it does not hold. Like it's not true that you can do this. In some other cases, you can do it. Some sort of conclusive results were as recent as 2015. And I have some results in this with 3 friends. So it's a group of 4 people. And we showed that if the level set looks like an ellipsoid in any dimension, so any odd dimensional ellipsoid, the answer to this question is yes. Like, can we find this? Yes, we can find. So yeah, so this is very active question. That paper I wrote was in 2022. And there's also been follow-up work. So ellipsoids are only one class of objects. You can imagine so many other, like what if I punched an ellipsoid? Now what? Right? So closing lemma is a very active area and been quite exciting recently. Okay, what other questions? There's this thing called Arnold's conjecture, which was a conjecture he wrote down slowly over the 60s. Like it's hard to make a question also precise, right? So, so a Hamiltonian flow, okay, the claim is any Hamiltonian flow has at least as many one-periodic orbits as the minimum number of critical points a function needs to have on the manifold. Sort of vague statement, but it's trying to classify what is the minimum number of periodic orbits, right? Before I was saying there's one, then how many are there? So this is giving you a lower bound. So let's write it. So number of periodic orbits, that's P of H, is greater than equal to, like this is the more refined version. There's some beta numbers called the Betti numbers. And this is the more refined version that people have been working on. Okay, so the only thing I want you to know about these beta numbers is it only depends on M, not on the omega form I'm putting on it, not on the function H. So that lower bound surprisingly only depends on the manifold. But this side clearly depends on H and also the omega. Okay, so this was a long-standing conjecture. He made it in 1960. I think he wrote it down in some form in 1964, and there was slowly work on it. So there was work first on 2 manifolds by a person called Yasha Eliashberg. Then there was work on things that are like torus. So sphere cross, like S1, sorry, circle cross circle cross circle, these type of things, people solved it. So slowly they were expanding what all manifolds it could be solved. A big breakthrough happened around 1990, where this person, did I put pictures? Huh. So Arnold is the person who made the conjecture. And the big breakthrough was by this person called Andreas Floer. So he sort of developed a totally new way of looking at these objects, which actually have like relations to string theory and all. So a very different way of looking at these orbits to conclude this for a very large class of manifolds. And then after that, it was sort of quickly generalized to cover all manifolds where you can ask this question. So yeah, so somehow like good questions can like lead to this like discovery of a whole new technique. And now this sort of technique we are using, which I haven't told you, Floer's techniques, and now people are using to do a lot of things. Okay, so out of this was born some interesting techniques also. Okay, so this is about minimum number of things. Now, this is the cool picture I wanted to show you. So this is from Quanta magazine, which is a magazine you should check out if you haven't heard about. They write like articles explaining recent developments in various sciences. It's pretty cool. And this is a picture of possible orbits. So I told you if you have a satellite, now some people have satellites, NASA has satellites, and they want to send it to Jupiter, Europa. So Jupiter is a planet, Europa is one of its moons, and they want to take pictures of Europa. This is what they want to do. And they have some constraints. So Europa has a lot of magnetic field, it seems. So you can't have, you can't send a satellite purely orbiting Europa. It will sort of combust and die. So you need to include Jupiter. And also it's a big mass nearby, so you have to include it. So in the Jupiter-Europa system, if you want to send your satellite, your orbits can look like there are a lot of options. So there's a picture I took from them. And so this actually, so this person, Agustin Moreno, we actually hung out for some time. So he does symplectic geometry. And he's been studying all these orbits from a very theoretical point of view and computing some things. And he didn't know that it has any applications. One day, this NASA engineer, she called him up and was like, I saw your paper and I think we can use it. And so now these two people have been talking with each other, and apparently people in NASA are using some numbers that we symplectic geometers were sitting and computing on our notebook to like check which orbits are actually feasible, like from a cost perspective and things like that. So it can actually have like actual implications also. So this was a recent development. I thought it was very cool. Okay, but there are other questions which have, at least for now, don't seem to have practical applications, but they're very interesting. So I want to talk about symplectomorphisms. What is a symplectomorphism? So there's a function from my manifold to itself, which is a diffeomorphism. That means it's differentiable and it's an isomorphism. So it has a inverse. So the function and its inverse both are differentiable. Roughly, that's the definition. So, and you want it to be in such a way that it preserves this omega form. So if it takes this point P1 to P2, omega at P1 and omega at P2 should match. Otherwise, it can't take it to the other point. So what am I saying? So suppose this is my manifold, this jelly bean type thing, and there are two vectors V and W here, and this function phi is taking them to some other vectors, is turning it around, pushing it, okay? The area I compute here and the area I compute that side after doing this should be outputted the same. And this should happen at all points. So that such a map is called a symplectomorphism. And you can put them all together into a set. And in fact, you can make a group out of it. How you make a group? You compose the functions. If you have one symplectomorphism and one more, composition gives you an operation on this. And it's a group because inverse is, I told you, no, diffeomorphism. So inverse will also have the same properties. Okay, so you get a group. And now as soon as you have a group, you're like, okay, what does this group look like? How big is it? What sort of group is it? So what structure does it have? Can you tell me properties? Is there a subgroup that I can like, it's enough to study that subgroup? So as soon as you have a group, you can ask about this. And this is not a very like well answered question. Like there are people actually working on all this, like how many components it has, what sort of maps are sitting in each component. So you can ask a lot of questions. So this is sort of a theoretical question that's of interest to many people in my field. So to study the entire group of these symplectomorphisms. The other fun thing is, so before we were talking about these Hamiltonian flows, right? So turns out if you take any Hamiltonian and then use its flow, it becomes a map that's a symplectomorphism. So that's one source of lot of Hamiltonians. So that is a subgroup sitting inside this. And now you can ask, is it a big subgroup? Is it a very small subgroup? What is sitting outside that subgroup? So all these questions are very like, and like you can easily find examples where people don't know answers to these questions. And there's something we are all thinking about. Okay. And lastly, these are my favorite objects. Things called Lagrangians. What are Lagrangians? So if you've taken some quantum mechanics, there's a different thing called Lagrangian. Warning, okay, this is different, but named after same person. Okay, so it's a half-dimensional submanifold. Remember we said symplectic manifolds are always even dimensional. So look at half of it. So n-dimensional submanifold, okay? So if it's like a 4-manifold, if you're looking at R4, there's something sitting inside which is 2-dimensional. So it's like a surface. So think about like a sphere sitting inside R4, okay? And you want it such that on that, so if you take two vectors sitting on that submanifold, you want omega to output 0. So what is it? So if V and W are vectors in that submanifold, now they're sitting along my submanifold, then the omega product is 0. Turns out just this much condition gives you very strict conditions on what this Lagrangian submanifold can be. So such a thing is called a Lagrangian. For example, I told you imagine a sphere inside R4. Immediately that's wrong. You can never have a sphere inside R4 that is, okay, Lagrangian plus some other things, but you can't have that object. Like already it can't look like a sphere, it has to be like a torus, or it has to have more topology. So these are very, we call them rigid objects. So it looks like they're small conditions, but then they end up satisfying way more. So what questions can, oh, they're examples. So inside R2n, it's not R2n, this is R4, okay? So it's spanned by x1, y1, x2, y2. And remember that matrix we did. So if I input x1 and y1, I'll get 1. And if I input something in x2 and y2 also, I'll get 1. But if I do x1 and x2, I'll get 0. So if I look at the span of x1 and x2 inside R4, I actually get 0 all the time, like when I restrict my omega to that subspace. So that subspace is a Lagrangian. Okay, but other things can happen. So on R2, if I take any curve, now remember that omega is skew symmetric. So on a curve, the only vectors that lie along that curve at a point are one vector and some multiple of that vector, right? Because it's like you can only like turn it this side or make it bigger or smaller. So that means that the tangent space at each point is a real, it's only one dimensional. And so if I input two vectors, if I put V and 2V inside omega, skew symmetric will give me that it's 0. So if I take any curve on R2, or in fact, remember the nice infinite cylinder we had, take any curve like this, you draw your favorite curve, that'll be a Lagrangian. So in 2 dimensions, this is not a very rigid condition. There are lots of things available. But as soon as you increase the dimension of your manifold, these become very interesting objects. And so we can ask questions like, given a symplectic manifold, my friend gives it to me. I'm like, what are the Lagrangian submanifolds in it? How big can they be? How small can they be? You have to also discuss what you mean by big and small. But these are questions. And like I was saying, right, in R4, you can't have a sphere. but you can have a torus. How many of these can be there? So you can ask in a specific topological class also whether you can have Lagrangians in your manifold. Oops. Okay, yeah, so this is also a very active set of classes, a set of topics that people study. In fact, I told you this was my favorite object, so I spend most of my time thinking about Lagrangians in R4. Like, it seems simple, it's the next thing to R2, but turns out it's very hard, and like I've written at least one thesis on it. So you can spend a lot of time asking such questions and trying to solve them. But there are lots of people working on it, and they develop different tools. Some names are like things like Floer homology, the same Floer we saw before. There's also some fancy thing called Fukaya category. And also this set of objects give you nice relationships to string theory. So there's another set of people in the physics world who are somehow studying, like the techniques that they're studying are the same, the questions they ask are different. I like Lagrangians, I'm looking at them, but they have other motivations. So yeah, this is also another active direction of study of like submanifolds that are interesting. Okay, I think that's the end of my talk. Thank you. I would like to end by mentioning two books written by these three people. One is called Introduction to Symplectic Topology by Macduff and Solomon. They have written a bunch of books, and but this is the first one. And there's also lectures on symplectic geometry by Ana Carrasta Silva. And these are nice books. They might have more prerequisites, but maybe at some point you want to like look at them, see some pictures. It'll be fun. Okay, and that's my email if you want to get in touch. Okay, thank you. Questions?